Everyone, today we will solve some problems from previous year question papers on AMVI examination. So here is the first question which was asked in 2003 examination. The magnitude of Coriolis component of acceleration of sliding block relative to link is V into omega, V omega by 2, twice V into omega, V omega square. Know that the correct option is option number 3, twice V into omega. Let us see how. We know that when a link rotates about some pivot point O and it has a slider P which is sliding along the length of the link. Now when the slider slides along the length of the link, it will also rotate with this link. We know that when the sliding velocity vector rotates or changes its direction, we have Coriolis component of acceleration, and magnitude of this component is given by 2 times the sliding velocity into the angular velocity with which the slider is rotating. So the correct option is option number 3, 2 into the sliding velocity into the angular velocity with which the sliding velocity vector is rotating. Now question number 2, in an engine mechanism, at what position of crank angle angular velocity of connecting rod is 0? 180 degrees, 90 degrees, 45 degrees or 0 degrees. Now we will solve this using equation. We know that angular velocity of connecting rod is given by this equation. Omega PC is equals to angular velocity of connecting rod is equals to angular velocity of crank into cos of theta, where theta is the crank angle, divided by n, where n is the obliquity ratio. Now omega PC will become 0 when this side becomes 0, and this will become 0 when cos of theta is 0, and we know that cos of theta is 0 when theta is equals to 90 degrees, because cos of 90 is 0. So the correct option is option number 2, that is 90 degrees. Now question number 3, which of the following is best example of higher kinematic pair? This was asked in 2005. Universal joint, shaft rotating in bearing, nut turning on a screw, and cam and follower. Now we know that higher pairs are the pairs having the point contact or line contact. In case of universal joint, this is the lower pair. Shaft rotating in a bearing has surface contact, so this is also the lower pair. Nut turning on a screw forms a screw pair, and we know that screw pair is also the lower pair. Now cam and follower has the point contact, so the correct answer is option number 4, cam and follower. Cam and follower is the higher pair because it has point contact or line contact in some cases. Now question number 4, which was asked in 2013, which of the following is inversion of double slider crank chain? Beam engine, elliptical trammel, Watt's indicator or quick return motion mechanism? No, double slider crank chain. We know that double slider crank chain has 2 sliders like this, connected by the binary link. So it has 2 prismatic pairs formed by these 2 sliders and 2 revolute pairs formed by this binary link, which is connecting these 2 sliders. Now the first inversion of double slider crank chain, which is obtained by fixing this link and changing the shape of the link, is the elliptical trammel. Let us call this as link number 1, this as link number 2, this as link number 3, and this is link number 4. So when we fix link number 1, we get this inversion. This is called as elliptical trammel, because any point on this coupler link which is connecting these 2 sliders will move along the elliptical path except the midpoint. You will remember this, any point on this connecting link, that is link number 3, will trace an elliptical path, and the midpoint will trace a circular path. So this is elliptical triangle. So correct option is elliptical triangle, which is the inversion of double-sided crank chain, because beam engine is the inversion of 4-bar chain, Watt's indicator the inversion of 4-bar chain, quick return motion mechanism is the inversion of single-sided crank chain, and elliptical triangle is the inversion of double-sided crank chain. And question number 5. When the crank rotates with uniform speed, it has only radial acceleration, only tangential acceleration, only Coriolis acceleration, or none of the above. We have seen, consider a link or a crank rotating about O. Suppose this crank rotates with the uniform angular velocity of omega radian per second. Now we know that for every particle P rotating with uniform speed, there exists centripetal component of acceleration, which accounts for change in direction of linear velocity of the rotating particle. So when this velocity vector v changes its direction while the particle p rotates about on the circumference of the circle, to account for the change in direction of this vector, there exists the centripetal or radial component of acceleration. Now suppose the omega is not uniform, it changes, so there will be angular acceleration of this link. Now when omega change, it will cause change in this v. So magnitude of v will change with change in omega. So to account for the change in this magnitude of v, there will be one more component of acceleration, which is called as tangential component, magnitude of which is equals to ft equals to r into alpha, and this accounts for change in omega or change in v, or when the link rotates with non-uniform speed, there is some acceleration or retardation alpha. Now the question is, the crank rotates with uniform speed, that means omega is constant. So when omega is constant, alpha becomes 0, this component is 0, and there remains only one component of acceleration, which is called as radial acceleration. So this is your correct answer. When any link rotates with uniform speed, it will have only one component of acceleration, which is radial component of acceleration. And tangential exists when the link moves with non-uniform speed. So when the link moves with non-uniform speed, when it has some angular acceleration, there will be two components of acceleration, radial or centripetal and tangential component. Now question number 6. Asked in 2013, consider the following statement: the degree of freedom of lower pair is always equals to 1. This is not true, because if we take an example of cylindrical pair, where a shaft rotates inside the bearing, this shaft may rotate or may slide inside this bearing, so it has 2 degrees of freedom. Even though it is a lower pair, it has 2 degrees of freedom because s and theta are independent. So this is not true. A ball and socket joint has 3 degrees of freedom and is a higher pair. A ball and socket joint has 3 degrees of freedom. This is true because ball and socket joint forms a spherical pair, but it is not a higher pair. Ball and socket joint ideally forms a lower pair. So this is not the correct statement. Number 3, Oldham's coupling has 2 prismatic pair and 2 revolute pairs. This is correct because Oldham's coupling is the inversion of double-sided crank chain, and double-sided crank chain has 2 prismatic pairs and 2 revolute pairs. So Oldham's coupling is like this. So this is one link, this is one link rotating with respect to another link, this is another link in the form of shaft which is rotating with respect to the same fixed link. So the shafts are rotating in the bearings. Say this is link number 2, this is link number 4. And link number 1 connects these two links 2 and 4 through the sliding pairs. So there are two sliding pairs between 1 and 2 and between 1 and 4, and two revolving pairs between 2 and 3 and between 4 and 3. So the correct answer is Oldham's coupling. Sliding pairs are 2 or prismatic pairs are 2 between link number 1 and 2 and 1 and 4, and revolute pairs are also 2 between link 2 and 3 and between link 3 and 4. So the correct answer is Oldham's coupling, which is the inversion of double static crank chain. Now question number 7. This was asked in 2011. Dynamics of machine deals with relative motion between the parts, neglecting the forces, or the forces acting on the parts of a machine, or the apparatus for applying mechanical power, or the number of interrelated parts each having a definite motion. These two are definitely wrong. Now we will compare these two. Now we divide the study of machines into two parts. We know that kinematics and dynamics. In kinematics, we study the motion between different parts of a machine, and in dynamics, we study the forces acting on those parts. Dynamics is further divided into two parts: statics and kinetics. So study of motion is kinematics, study of forces is dynamics. Study of forces, assuming the parts of the machine are at rest, is statics, and study of inertia forces comes under kinetics. So the correct answer is option number 2. Study of forces acting on the parts of a machine is nothing but dynamics. Next is question number 8. The lead screw of a lathe with a nut forms a rolling pair, sliding pair, screw pair, or turning pair. This was asked in 2011. It's a very simple question. A lead screw of a lathe with a nut forms a screw pair. In question number 9, the the relation between number of pairs P forming a kinematic chain and the number of links L is L equals to 2P minus 4, L equals to 2P minus 3, L equals to 2P minus 4, and L equals to 2P minus 5. The correct option is option number 3. L equals to 2P minus 4. You have to remember this. There are two relations. We know that L equals to 2P minus 4 or J equals to 3 by 2 L minus 2. Using these two relations, we find the type of the kinematic chain. We have seen this. Using this two relation, we identify the type of mechanism. So this equation establish a relationship between number of links and number of lower pairs in a mechanism. So correct option is option number 3. We have to simply remember this. Now question number 10, asked in 2011. The component of acceleration perpendicular to the velocity at the given instant is called. Now we know that the particle P rotates in a circular path, it will have two components of acceleration. So if omega is the angular velocity of the particle, it will have centripetal component of acceleration or radial component of acceleration, which acts along the radius of rotation and it is directed towards the center of rotation. So this is parallel to radius of rotation and it acts towards the center of rotation, centripetal or radial acceleration. So if we consider OP as a link, centripetal component is parallel to the link. Now this point will have some linear velocity v, which is equals to r into omega. So for the change in direction of this v, we have radial acceleration, and for change in magnitude of v, we have another acceleration called as tangential acceleration. Ft equals to r into alpha. Now nothing is mentioned in the problem whether the particle is rotating particle or it is moving along a linear path. the component of acceleration perpendicular to the velocity at the given instant is called. Which velocity? They have not specified whether to consider this linear tangential velocity. Okay, so we will not take this because they have not specified in the problem that whether the velocity is linear tangential velocity or the particle is rotating. So we will assume pure linear motion. So consider a slider sliding on the rotating link. Suppose the slider is moving in upward direction, so it will have the sliding velocity which is parallel to the line of stroke of the slider. It will have some acceleration which will act in the direction of this velocity if velocity v changes. So this component of acceleration is parallel to this. Now when the link rotates, the velocity vector will rotate with this link. So there will be Coriolis component of acceleration, and we know that Coriolis component of acceleration is always perpendicular to the velocity vector, which is equals to twice v into omega. So this component is perpendicular to the velocity at all the instances. So the correct answer is Coriolis component of acceleration, because radial acceleration and tangential accelerations are only for particle executing circular motion. So the component perpendicular to the velocity is Coriolis component only. Now question number 11. The direction of Coriolis component of acceleration is obtained by. I will directly give the solution. We know that when the slider slides along this link, it will have the sliding velocity. Now when this velocity vector of slider p rotates with this link, there is Coriolis component of acceleration whose magnitude is twice vs into omega. And to find out the direction of this component, what we do, we rotate this sliding velocity vector in the direction of angular velocity of the link through 90 degrees. Now for this case, let us suppose that velocity of slider is upwards. That is, slider is moving in upward direction and the angular velocity of this link is clockwise. So what we will do, we will take this sliding velocity vector vs. We will rotate this vector in the direction of omega clockwise about its tail to get the direction of Coriolis acceleration. So the correct option is, we rotate the velocity vector v of the slider at 90 degrees in the same direction as that of omega. Option number 2. The question number 12. In the figure shown below, the number indicates length of links. Which of the following is crank rocker mechanism? Now this problem is to be solved using Grashofian law. This was asked in 2017. This is very important question. Now for that we need to study the inversions of 4-bar chain. For that I will draw one tree diagram here. So for a 4-bar chain, if length of shortest, the sum of length of shortest and longest link is less than the sum of length of other two links, then the linkage is called as Grashofian linkage. If S plus L is greater than P plus Q, that is, sum of lengths of shortest and longest link is greater than the sum of length of other two links, these are called as class 2 mechanisms or non-Grashofian linkages. And if S plus L equals to P plus Q, these are called as spatial class linkages. Now I am telling you how to solve such kind of problems. First of all, in a mechanism, if S plus L is less than P plus Q and you fix the shortest link, if you fix the shortest link, we get double crank mechanism. What we get? We get double crank if we fix the shortest link. If you fix any one of the links adjacent to the shortest link, If I fix link adjacent to the shortest link, I will get crank rocker mechanism. The same will be obtained when we fix this link. If we fix link opposite to the shortest link, we get a double rocker mechanism. What is? This is how we will identify. Next, if S plus L is greater than P plus Q, all the inversions obtained, regardless of the type of link you fixed, all the inversions will be double rocker or rocker. All the 4 inversions will be double rocker, regardless of the link you fix. Now for S plus L equals to P plus Q, there are 2 cases. In the first case, we arrange links with similar length opposite to each other. For this, regardless of the type of link you fixed, you will always get double crank mechanism. कौन सा भी link fix करो, you will always get the crank mechanism. Number 2, there is second case of deltoid linkages, in which 2 adjacent links are of same length. So this is short and this is long, placed adjacent to each other. If you fix any one of the shortest links, you will get double crank mechanism. Okay, this or this, you will get 2 double crank mechanism. And if you fix any one of the longest links, you will get crank rocker mechanism. Okay, now how to solve this problem? The question is, identify the type of mechanism, which is crank rocker mechanism. Now for that, first of all, we have to identify the class of the mechanism by solving this equation. So S is 5, shortest link, longest link is 9, is equals to sum of other 2 links, 7 plus 6. So 9, 10, 11, 12, 13, 14 equals to 13. So S plus L is greater than P plus Q here. So this is double rocker. This is non-Grashofian linkage. This falls into this category where all the inversions are double rocker. So this is also double rocker. We want crank rocker. So this is not our answer. Number 2, S plus L, 4 plus 9, 13, and 7 plus 7, 14. So S plus L is less than P plus Q. This is Grashofian linkage. And the shortest link is fixed. So in Grashofian linkage, when we fix the shortest link, we get double crank mechanism. So this is crank, not crank rocker. So this is not our answer. Number 3, yes, 5 plus L, 15, and 7 plus 9, 15, so 16, no? 16. So S plus L is less than P plus Q. The link opposite to the shortest link is fixed. So this is rocker mechanism. This is not our answer. We want crank rocker. Now let us try this. Shortest link is 4, longest link is 10, so 14. Sum of other 2 links is 15. So S plus L is less than P plus Q. This is Grashofian linkage. Link adjacent to the shortest link is fixed. So this is crank rocker mechanism. So this is the correct answer. Option number 4 is the correct answer. This is Grashofian linkage because S plus L is less than P plus Q, and the link adjacent to the shortest link is fixed. So this is crank rocker mechanism. So to solve such kind of problems, first of all, you have to identify the class of the mechanism, and then you will look for the link which is fixed. You will remember this tree which will help you to solve such kind of problems. Now link number 13, pendulum pump is the inversion of single slider crank chain, because pendulum pump is formed when we fix, say this is link number 1, 2, 3 and fix link number 4. When we fix link number 4, we get pendulum pump or hand pump. So this is the inversion of single slider crank chain. Now problem number 14, asked in 2017. In a pantograph, all pairs are turning pairs. This is the correct answer. because we know that in pantograph we have a parallelogram. We extend one of the links, we pivot it, so all the pairs are turning pairs. All the pairs are turning pairs. So this is pantograph is a lower pair mechanism. All the pairs are turning pairs. Now question number 15. In a kinematic chain, a quaternary joint is equivalent to 3 binary joints. This is the correct answer. Binary joint is defined as the joint where 2 links are connected. This is a binary joint, one binary joint. Now if 3 links are connected to a connection, this is one ternary joint. This corresponds to 2 binary joints. So total number of binary joints at a particular connection are determined. Total number of binary joints at a particular connection is determined by this equation. Total number of links connected at that connection minus 1 are the total number of binary joints. So in case of quaternary joint, there are 4 links connected at a joint. So 4 minus 1, so this corresponds to 3 binary joints. So you will use this equation. Now question number 16. The condition of correct steering for a Davis steering gear mechanism, where alpha is the angle of inclination of the links to the vertical, B is the wheelbase, and C is the distance between pivot. Now we have only 3 equations for steering gear mechanisms. This is the front axle, the back axle. This is the wheelbase L, width W. If you take the turn, so let phi be the angle turned by outer wheel, and theta is the angle turned by inner wheel. The condition of correct steering is cot of phi minus cot of theta equals to W by L. Fundamental equation of correct steering. This is the first equation you will remember. Phi is the angle turned by outer wheel, theta is the angle turned by inner wheel, W is the width, and L is the wheelbase. Now second, for Davis steering gear mechanism, we have like this arrangement. We have like this arrangement. These are the wheels, front axle. Bell crank levers are mounted with sliding pairs connected using a track arm which is constrained to be horizontal. This angle is alpha. Now for Davis, there is tan of alpha equals to W upon twice L. And for Ackermann, we have tan of alpha equals to sine of phi minus sine of theta divided by cos of theta plus cos of phi minus 2. So not a single equation is of this kind. This is for Ackermann. So your correct answer is tan of alpha equals to C upon twice B. Now question number 17. The instantaneous center of slider moving on a curved surface lies at infinity. Their point of contact, center of curvature of the curved surface or pinpoint. We know that for a pin joint, their eye center lies at the connection. For the slider, whose center of rotation is at infinity, their eye center lies at infinity. So for a curved path, if the slider is sliding along this curve, its center of rotation will be obviously at the center of this curve. So the correct answer is option number 3, center of curvature. In the next lecture we will solve some more problems. Thank you.